start. So, good afternoon, everyone. My name is 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧. I'm a fourth-year PhD student, and today I would like to present you some of my research. In this case, a work entitled as topological derivative in constraint optimization problems via the null space algorithm. This work has been supervised by Dr. 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧 and Dr. 𝗕𝗦𝗧𝗧𝗥𝗔𝗕𝗦𝗧𝗧. Let me start by introducing a bit myself. I am a null space engineer. I did my bachelor's degree in null space technologies engineering in 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧 in UPC. Therefore, after that, I started working as a technical engineer in a company and at the same time doing my master's degree in aerospace engineering, again in 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧 in CIMNE campus. And after that, I met Dr. Alex, and I started a master's thesis as a way to start my research in my ulterior PhD in topological optimization with ideal manufacturing constraints. And with this master's thesis, I started later my PhD in structural analysis in UPC CIMNE from 2022 and hopefully finishing in 2026 with Dr. Alex and Dr. 𝗕𝗦𝗧𝗧𝗥𝗔𝗕. I'm investigating inside the camps group from CIMNE. And in this case, I will present you some block of my research. In this case, more focused in the algorithm used to solve the topological optimization problem. And one algorithm we are using. This is the outline of this presentation. I will start presenting a bit the motivation of this study, then the methodology employed to solve the problem, some applications, and finally the conclusions. So why topological optimization? So let's focus, for instance, in the transport industry, in aerospace, or automotive industry, where is a clear need to obtain Lagrangian structures in order to reduce the field consumption and then the environmental impact. And this is because in aerospace or in automotive industry, the designs we can find nowadays are very traditional designs. For instance, in the case of the features of an aircraft, there are a disposition of horizontals and vertical stiffeners, and this design is very traditional. So imagine we have some black box, in this case called topological optimization, which allows us to, from these original designs, obtain these new ones, where some complex shapes and complex volumes have been introduced in the domain in such a way that new structures with less weight are obtained, able to fulfill the same distribution of external forces and constraints, and therefore reducing this field consumption. And how does this topological optimization tool work? So given a design original field with material, for instance, this cantilever beam, clamped in the left side and with a point load in the right side, the objective is to reduce continuously the mass of this domain in such a way that some functional J is minimized and some constraints are fulfilled. In order to reduce this mass, we define the characteristic function G, which is the design variable of our problem. It's a binary variable that basically sets ones and zeros, ones in material domain and zeros in void. So we start with everything equal to 1, and we put zeros in a continuous way in order that some functional is minimized. For instance, one common function is a compliance, which is defined here. Is the product of the external forces times the displacements obtained by these forces. Is a measurement of the flexibility of the domain, and therefore by minimizing this compliance, we are maximizing the stiffness of the design. And a common constraint is the volume, so at which extent we are reducing the mass of this domain, and at each step maximizing the stiffness. And of course, we have also PD constraints, for instance, the elastic problem. However, this starting point, the problem is backposed, since we are dealing with a discontinuous characteristic function. So here T is 0, and then it's 1. But in the boundaries between a white and a black region, we find an infinite gradient, and this is not good for optimization purposes because we are usually dealing with gradients. So we have to propose some alternatives. In topological optimization, we usually find, for instance, density, which is basically the continuous version of it, where with the apparition of gray areas in the interfaces between black and white regions. And then we have to think about the need to interpolate the elastic properties in these gray areas. We have to characterize them. It can be understood as some sort of composite material. And one way to interpolate this elastic tensor is by using the CIMNE method, which is this expression here. And on the other hand, we can find also level set where we still work with the original characteristic function, but now by means of a surface, a level set function, and more specifically, in function of the sign of this level set, we retrieve directly the black and white areas. With density, we can use typical algorithms to solve the problem. And with level set, it's a bit more complicated. We find shape and topological derivatives as a way to update this level set function. In this presentation, I will focus mainly in topological derivatives or level set. So far, we have a problem with a PD constraint, which is complex. Also, the objective function is non-linear, since it's a flexibility, it's a non-linear variable. And in topology optimization, we usually have to deal with a lot of constraints, or in specifically local constraints. For instance, in my research, I'm usually dealing with these four. On one hand, minimum length scale constraint. In order to manufacture this design, for instance, with additive manufacturing, we have to ensure a minimum thickness locally in the domain. Also, overhang constraints. And we have a boundary with a lot of overhang angle. It can fall during the deposition process. In field topology optimization, which basically means to ensure a fraction volume control locally in all points of the domain, or stress constraints. All these kind of constraints are constraints that must be fulfilled locally. For instance, we can ensure these constraints for different subdomains. In the end, we obtain a problem which objective function is nonlinear. We have a lot of constraints which are also nonlinear and PD constraints. Overall, the problem is extremely complex to solve. And focusing, for instance, in 3D, where we use the finite element method to solve the problem, for instance, the elastic problem, we may have up to 1 million degrees of freedom. And therefore, overall, we must refer to advanced optimization techniques to solve this problem. One common technique is Augmented Lagrangian method, which currently works for both the density and level set methodologies, but it has a problem and is parameter dependent and is very slow. It needs a penalty parameter for each constraint, and we have to perform a lot of numerical experiments to calibrate the whole problem, and it's case dependent. And since completing a simulation in 3D may take up to 24 hours, it's not efficient to use Augmented Lagrangian. Then we also find in Taylor point methods. In the same sense as Augmented Lagrangian, it needs, again, a bit of tuning of parameters. Then we can also find MMA, which is, it's well suited for density. I mean, people from density methods use a lot of MMA to solve the problem. I mean, in general, works well. There is also some parameters to calibrate, but in general, it's good, but it just works with density. And then, recently, we can find an algorithm which is called Null Space, proposed by Florian Febon in 2020. And he basically looked for an algorithm which is free of parameters and currently works for density and level set with shape derivatives, but it has not been extended yet to topological derivatives. So given the impact that this work had in the topology optimization community, our focus will be to extend precisely this Null Space algorithm also to topological derivatives in order to bring to the community an algorithm which is able to handle density and level set and without the need to perform a lot of numerical experiments. Okay, so this is the objective of this part of my research, and also able to handle multiple local constraints. So now let's go to the methodology. Before defining the Null Space, I think it's a very good idea to revisit the gradient descent algorithm. So imagine we want to minimize a function j in function of x. X could be, for instance, the characteristic function, density, level set. So we have 1 million of unknowns. Then this problem, since j is nonlinear, is non-convex. We have a lot of local minima. And it's very hard to solve. And one simple or efficient approach is to use the gradient descent algorithm. This approach doesn't guarantee a global optimum. It's a local optimum approach, but it's the only way we have nowadays to solve the problem. So imagine the black curve is a kind of representation of this j, and we want to find this local minimum. So this point where the gradient of j in function of x is equal to 0. One way to proceed is, given an initial guess, build an auxiliary quadratic approximation problem, which is something similar to a Taylor expansion, but the quadratic term is not the Hessian, it's a quadratic term with some parameter tau. Let's see here in more detail. And so let's approximate a parabola tangent to the first point, such that the minimum gives you a point which is below the original point. And by solving this sequence of quadratic problems, we will end up finally in the local minimum point. So we are not approximating, but we are solving the problem by a sequence of auxiliary problems of this sense, where a parameter tau is introduced, and basically this parameter tau scales the parabola. For the lower the tau, the more the smallest the parabola, so the shortest the step we are doing, and the higher the tau, the longest the step. So as a original problem, in order to solve this auxiliary problem, we have to find some xk plus 1 such that the gradient is equal to 0. And this problem can be solved analytically, and basically gives you this formula here, which is the gradient descent algorithm, as most of you will know. For some small tau, we can step by step decrease the function until finding a local point. Let's now talk about the null space, where now we are not going to minimize a functional, we are going to minimize a functional, but subjected to as a set of constraints. Let's start, for instance, with a set of equality constraints. These can be expressed as a saddle point problem of the Lagrangian. So we have to solve min-max of the Lagrangian, where again, this Lagrangian functional is nonlinear in the sense of x, no? Of the primal value. So why not to propose a similar approach as the gradient descent algorithm? Let's approximate this problem as a sequence of quadratic problems, auxiliary quadratic problems, in the sense of x. And it's very similar as the previous one, but in this case, I have used a parameter for the gradient and another parameter also for the quadratic term. Later, we'll see why we did this and which contributions did they have. But we can see, so if we take this quadratic expansion and then we extract common factor from the Lagrange multiplier, we can see that this is equivalent as a SQP approach, so a sequential quadratic programming approach, where we substitute the original problem as a sequence of quadratic programs. A quadratic programming problem where the objective function is quadratic and the constraints are linear. So the objective function is a quadratic expansion of the original objective function, and the constraints is a linear expansion of the original constraint. And again, this problem can be solved analytically. We can write a canonical form for this problem if you want. And then how to solve this problem? We have to solve the optimal condition with x and with the Lagrange multipliers. This is a system of equations that are easily solved analytically, yielding the result. It's very interesting to know that the Lagrange multiplier, in this case, I have split the Lagrange multiplier in two terms, lambda j and lambda g. Both depend in k, so are explicit formulas. We can compute the Lagrange multiplier at each step before computing xk plus 1. This is a positive thing. And then the final formula is something really similar to the gradient descent algorithm. We have again some line search multiplied by some direction. The difference is that this direction is the sum of two directions. Let's discuss a bit the physical meaning of each of these directions. In red, this direction here, which has this formula, is called null space because basically it's a projection of the gradient of the cost function in the null space of the gradient of g. In fact, maybe some of you are familiar with projections and you can identify this term as a projection operator. So we project the gradient of j in the kernel of the gradient of g, and therefore we are minimizing the cost function while keeping tangent to the constraints. This is the tangent space of the constraints. And on the other hand, we have the range space flow, which basically is the opposite, is a direction which aims to get closer to the constraint at each iteration. And so by a combination of the two directions, we obtain the complete volume flow. So the top parameter that I used in the auxiliary quadratic approximation problem appears basically as a line search again, as the integrating descent algorithm. And the other parameter that I used in the quadratic term appears multiplying the range space flow. And this parameter basically what does is to scale the relative length of the vector of the range space vector with respect to null space. So I have obtained a control to scale the range space with respect to the null space. And more specifically, I can rewrite the eta parameter like this with another this is the only user-defined parameter, eta star. And we will see in the next slide that it has some intuition. It will be the only parameter, and the role of this parameter is precisely this, to scale the range space with respect to null space flow. And here tau is again the line search that must be enough small in order to decrease the Lagrangian function in this case. So yes, as I was saying, this eta star has the following idea. With eta star equal to 1, the idea is to give the same priority in both directions, the direction that minimizes the function and the objective function, while keeping tangent to the constraints, and the range which approaches directly the constraints, also in an orthogonal direction. And then with 0.5, we give twice importance to the null space, and with 2, for instance, we give twice importance to the range space set. And that's why this algorithm looks for free parameters, because the only parameters that has are intuitive for the user. So until this point, we have solved a constraint optimization problem with equality constraints. But what about inequality constraints? We can do a similar idea. So we can, again, solve the problem by a sequence of quadratic programs of a quadratic approximation of the cost function and linear extension of the constraints, in this case, including inequality constraints. And now this auxiliary quadratic problem is not longer here, it has a typo, it's basically mean xk plus 1. Max lambda and mu larger or equal to 0 of the Lagrangian, which depends on tau and eta. And instead of solving the optimality conditions, I have to solve the Karush-Karantakel conditions at each step. So I basically have to add the complementary conditions for this new Lagrange multiplier corresponding to the inequality constraints. Okay. And this is an application of the null space, a small application, like a toy example for analytical problems. Analytical problems basically means problems where the objective function and the constraints are analytical functions like paraboloids, planes, hyperbolas, and so on. So I have solved 3 cases with different eta stars to see more or less how the path of the optimization process behaves. For instance, in the problem number 1, when we see the objective function tends to be minimum in this direction, and we have this set of feasible solutions. The higher the eta, let's say the more orthogonal the path becomes towards the boundary of this constraint. And in fact, in case 2, we can see this effect with more detail, since with a low eta, the direction basically is dominated by the null space, which aims to minimize the cost function. So the optimization wants to go to the minimum point and later fulfills the constraint. And as eta star increases, the optimization process prefers to first satisfy the constraint and later minimize the function. In this case, the same solution is obtained because we have just one solution, so it is independent of the choice of the eta star. But in the path, in topology optimization, we will see that in function of the eta star parameter used, we can obtain different local points. Okay, so far we have the first ingredient, which is the Null Space algorithm. But at the beginning of the presentation, I said that we're going to use topological derivatives. So we're going to extend this algorithm from density to also level set with topological derivative. First of all, let's define a bit what is the idea of topological derivatives. So imagine, again, a domain characterized with a characteristic function g. And now, imagine we can insert an inclusion of this shape at some coordinate hat x. The topological derivative is basically the field or the function that fulfills the following asymptotic expansion of the cost function. So given this inclusion, I can define, I can transform my original characteristic function to another characteristic function which depends in a radius epsilon of this inclusion. And then the topological derivative is basically a function that fulfills this expansion, where this f is a corrector function. But if we substitute basically from this expression the topological derivative, we see that we obtain something like this. And if we take the limit when epsilon goes to 0 of this expression, we obtain something quite similar to a derivative. So that's why this function, this is a function because it can be evaluated at any coordinate x on the full domain. This is why this can be understood as the topological derivative of the cost function j. Then the optimality condition is the following. This is obtained from the work of Samuel Amstutz from 2006. So if we want to arrive to a point where the j is minimum, in this case, we function of the level set, we have to arrive to some point where for any coordinate x, if I introduce a perturbation of radius epsilon, the cost function always increases. That means the topological derivative is positive in all coordinates x of the domain. How is this translated to the level set case? Well, we will introduce a mathematical transformation or mathematical tool to solve this problem with level set. This is called, by the way, Slerp, this approach. Now let another function be defined like this, topological derivative with a minus for the points where the level set are negative and positive otherwise. And this is done in order to convert this original optimality condition to this new one, where basically we have that when this new function is negative, then the level set is negative, and when this new function is positive, then the level set is positive. So we convert the original optimality condition, topological derivative greater than 0, to another condition where the level set must be parallel to this new function, which is basically understood as topological gradient. Okay, and this is an angle condition. We want to find a level set such that in the optimum is parallel to this new topological gradient. And we solve this with a fixed point algorithm. This is basically an interpolation of the level set in a manifold between a level set in iteration k in our current iterate and the topological derivative in our current iterate. We are interpolating in this manifold the new level set, and we keep repeating the process until convergence. This is used to find a minimum point for some functional j, so an unconstrained minimization problem. How is this expanded in the Null Space algorithm? So we have seen so far that for gradient methods, we find for unconstrained optimization problem the gradient descent formula, and for Null Space a very similar formula where basically instead of computing the gradient of the cost function, we compute the gradient of the Lagrangian of this Null Space expansion. So since for topological derivatives, we found this Slerp equation for the original cost function, And with this analogy, why not to use the same Slerp formula, but computing the topological derivatives for the Lagrangian expansion using the same parameters as we used before for the null space, the tau and the eta. And this is precisely what we have done in this work. And well, this is the algorithm. Basically, we have an introductory block where we define the initial guess, previous calculation, and so on. Then we enter in the huge loop, which is related to the convergence of the global problem and fulfillment of constraints. And inside this block, we have a first block to compute the dual variable, as I said before, it's explicit, so we can compute it before updating the primal variable. And then a loop where the primal variable is updated by searching the line search, so tau, enough small to decrease the Lagrangian function. So let's see some applications. Let's solve two topology optimization problems in the macroscopic scale. I will focus in minimum compliance problems and compliance mechanisms. Minimum compliance, as I presented in the beginning of this presentation, is basically the design of structures with maximum stiffness, because we're minimizing the compliance, the internal energy of the domain. And on the other hand, we can find also the design of compliant mechanisms, where basically we are creating mechanisms with hinges points in order to invert the displacements of the design in certain location and obtaining negative stiffness designs. In all these problems, I will consider a volume constraint and, of course, the TP constraint related to the elastic problem. Let's start with the cantilever beam. I have solved the cantilever beam for 3 different values of the eta star. Remember, eta star is the intuitive parameter for the user. So the lowest eta star, we can see so the lowest eta star, the more time it takes for the volume to arrive to 0, so to the volume target, the volume constraint. But the compliance is minimum, is the lowest from the 3 cases, because we're giving a lot of importance to the cost function. And the highest eta star, we can see the volume goes directly, so the volume constraint goes directly to 0, but the last compliance is worse because we're giving more importance to the constraint. In general, for all cases, the problem is successfully solved, but we can see a small issue, and are these oscillations near the target region. And this is a curious thing, because if we compare this approach, for instance, with gradient methods, for instance, an analytical problem, we can see that the problem is the evolution of the optimization process is in generally smooth. And why? Why is this smooth? I didn't explain it before, but I will introduce you now why is this smooth. And basically, imagine, so I have my solution, and imagine that now I perform a linear expansion, a linear Taylor expansion of the constraints, which look like this. And I introduce in this expansion the solution of the null space algorithm. And I obtain something like this. If I want to control the amplitude of the constraint curve, we agree that in absolute value, the term multiplying the constraint in previous iteration must be smaller than 1 in order to obtain a contractive behavior of the curve. And then we can see that the eta must have a maximum value of 2/2. So we have a control of the maximum eta that we can use in order to solve the problem with this smooth control of the process. But this is not the case for topological derivatives at this point. So for analytical problems and density, we can see that the evolution is smooth. It doesn't oscillate near the target value. But for level cell, with topological derivative, is oscillating a lot. This is in for instance, the Lagrange multiplier, also the constant. We can see this behavior in other examples. This is a 3-dimensional cantilever beam. Again, we can solve the problem successfully. We obtain for both cases. In one case, 40% of volume, and in the other case, 20%, which is a low volume. So null space is also able to arrive to low volumes designs. But again, near the constraint target value, it oscillates. But the solution is okay. So the optimum is okay. It's just a matter of the numerical stability. This is another example. This is a bridge example, and also typically in topology optimization. Again, I have selected 3 different values for eta star, and the highest eta star, the fastest the volume constraint goes to 0, and vice versa with the compliance. The lowest eta star, the better the compliance obtained in the end, so small minimum. We can see also the overshooting here is greater than in the first case. The conclusions are the same, the results are good again, but we cannot avoid these oscillations near the optimality conditions. And this is the gripping. In this case, we don't have problems of oscillations because the final result, let's say the final value of the density or the level set is below the volume constraint because it's an inequality constraint. So the constraint is inactive, and in the end, we will retrieve a pure unconstrained optimization problem. But it's nice because we can see how we can obtain these designs with hinges and where the displacements are basically inverted in the output region. So we can also solve these kind of problems. And just to finish, let's solve a problem with multiple constraints, which is a bit the motivation of null space. And a common benchmark is a multi-load bridge, which objective is basically the minimization of a volume functional subject to a set of compliance constraints. So we have to deal with a lot of elastic problems. In this case, we have to solve 9 compliance, so 9 elastic problems at the same time. Here I have this bridge with these 9 load cases. It doesn't mean that I'm considering all these loads at the same time. I'm considering, for instance, the compliance with this load, then the compliance with just this load, the compliance with just this load. So I have a lot of constraints, separate constraints. And with this example, I will see if null space actually works well with multiple constraints. Okay, here are the solutions with just the load case in the middle, then 3 constraints of compliance, and then all 9 compliance constraints. And we can see that the solution is obtained successfully, since for the case where I have all load cases, I have obtained like small and slender bars in order to withstand these additional problems. But we can see the oscillations around the constraint target are very, very high. And then this is a trade-off of this approach. Okay. But then, again, it's a matter of numerical stability, but the problem is correct, successfully solved. Just to finish, I will introduce you some strategies we have been working for this maximum meta to solve this oscillation issue. So we recall for density, we have this maximum meta of 2/2. And we can study a bit how this maximum meta behaves. So as I explained a bit at the beginning and of the presentation, for gradient methods, we start with an initial guess and then some gradient, which is relatively high because we are in a region with a lot of, let's say, slope with a high slope. So we need a tau at the beginning, a tau enough small. And once we arrive to the local minimum point, later tau can increase. Once we arrive to the local minimum point, the gradient of J is 0, and then tau can increase up to infinity, for instance, because we arrive to the convergence. We always try to increase tau in order to go as fast as possible, but we have to keep a control in order to avoid the obtaining of some xk+1, which is outside my neighborhood. But this is the idea. I start with a small tau to advance slowly, and then here I can increase it. This is translated as an eta, maximum eta, which is high at the beginning, and in near convergence, it starts to decrease to 0. or to a very small number. So our strategy was, okay, why not to propose some similar behavior, in this case like this Slerp function. So defining a maximum eta, of course, this is defined by the user in this case, in this starting point. We start defining a high eta, and then once we are getting near optimality conditions, that means when the angle between the level set and the topological gradient is becoming near to 0, let's start decreasing this value until some small value, some value near to 0. And here I can show you some updated results using this approach. The cantilever beam and the multi-load bridge with 3 and 9 loads. And we can see that now the results are successfully obtained, and the oscillations near 0 are decreased with a high magnitude. No? For instance, the multi-load bridge with 9 loads, we start at the beginning with a lot of oscillations, but in the end, we have very, very low oscillations. So it's a great advance in this regard. And it's also important to mention that the problem is solved with just one parameter, which is eta star, in contrast with Augmented Lagrangian, which needs to define the penalty parameters for all the constraints, and we need to perform a lot of numerical experiments to find the actual parameters for each of these constraints, each of these penalties of the Augmented Lagrangian. Okay, so as conclusions, the Null Space algorithm now is completely versatile. The main idea is to use the same Lagrangian function expansion for the Slerp updated formula. And this is the first time that topological derivatives are used in this Null Space algorithm. We have shown some progress in topology optimization with less tuning, and then we are advancing towards this idea of replacing the Augmented Lagrangian by another optimizer, which has less tuning parameters. And as an ongoing work, we keep studying these oscillations near constraint target. Maybe we can find a better formula for the maximum eta. Or if it's necessary to discretize more eta, not only a global eta for all the constants, but probably to study the possibility to use different etas for different constants. And that's all. Thank you so much for your attention. And just I would like to mention this work is financed by Generalitat de Catalunya with 𝗔𝗕𝗦𝗧𝗥𝗔𝗖𝗧. And this work is available in a GitHub code repository called CIMNE. And here I give you the link if you're interested. And now you have any questions, do not hesitate to ask. Thank you.
Nobody's working. I can be chair if you want me to be chair. Thank you, Jose.
Okay, thanks for your presentation. Now you showed us for various examples that this parameter eta star, different values of eta star provided qualitatively different results, qualitatively different geometries regarding number and thickness of members. Okay. Which one would you say actually manufactured?
Okay. Well, in the sense of manufacturing, in this work, I have not used manufacturing constraints. So in general, none of these could be manufactured. So let's see, for instance, this result. So none of these structures fulfill a minimum scale constraint. So we couldn't manufacture any of these. We have to include ID manufacturing constraints, which is in part of another part of my research. I would say, as a trick, the highest the eta, so at least in problems with minimum compliance and volume constraint, the highest the eta, the fastest you go to the volume constraint. And in general, since the optimum is a bit worse, you are obtaining thicker bars in this case. For instance, let's see the cantilever. But this is not of course, this is not an ideal thing. this is not an ideal thing because we should include these additive manufacturing constraints, but as eta is increasing, you can see here we started with a lot of bars and we are converging into results. This simulation maybe is not completely converged, but these bars would disappear. You would obtain just 2 thicker reinforcing bars. So I would say with high beta.
So that I think I had the same question as you when I saw this image. Like I think the question is, which one do you think is the good solution, no? Or the best solution?
Yeah, exactly. When I say which one would you manufacture, I'm not thinking of actually manufacturing it.
How do you decide which?
Yeah, which one is your solution?
Okay.
Like it's true that the parameter, you completely understood the effect of the parameter and how it's working, but then one that comes from outside might think, but which one is the good solution or the best solution?
Okay.
No? I think that was the question, and I also had the same question, yeah.
So if we think in the best solution is always the one that gives you the minimum compliance, because it's the one with more stiffness, no? In this case, the first one, the one with 2 points.
The more classical one.
The more, yes.
That you would expect.
Yes, exactly. If I could, I will always manufacture the one with minimum with the lowest compliance, if I can. But but it's not clear. Maybe in another problem, I see that the one with the best optimum, maybe it's with high gas eta star, so it's not clear. It's arbitrary thing, but in general, I have obtained.
So you do not see a correlation between lower eta and higher.
Yeah, sometimes no. In problems of macrostructures and minimum compliance, generally, I would say the lowest eta star, the better the final compliance, because you are going slowly in minimizing the compliance, so it should be better. But they have found other situations where it's not necessarily a relationship. Maybe the 3 compliances are very similar. So.
In the end, it's logical, right? Because a lower eta star means it's what you just said. So it also depends. Well, the constraints in the end also are important. Like one thing is the theory, you know, what would I think is the best solution, and the other is what is the best solution that can actually be constructed.
Then in the bridge, for instance, we have the compliance and the constraint. So this is the reverse. In the multi-node bridge, I prefer to use a high eta because I'm giving more importance to the compliance, and then I'm maximizing the stiffness with high etas.
Can you put that?
Yes. Well, here in this problem, I minimize the volume and I implement a lot of compliance constraints. So if I give more importance to the constraints, I'm giving more importance to obtain a design with maximum stiffness rather than minimizing the volume. So maybe I'm more interested in this case. It depends in my application, of course, but if I'm interested in maximizing the stiffness, in this case, maybe I should select the high eta. In this case, the eta is the same, but I used a high one, no? 5. I'm giving a lot of importance to the compliance. And then I'm obtaining these kind of designs where we can find new slender bars in these versions. But of course, this cannot be manufactured. We should implement manufacturing constant because these beams are very, very slender.
Okay, another question. Yes. Now, I missed, so you have like 2 phases, you have black and white, you have void and material. How do you, I mean, do you have something like a pixel size or a cell size in your model?
Yes. Yeah. Yes. We solved the elastic problem with the finite analytic method. So yeah, I implement a mesh and then I define this characteristic function of ones and zeros in the nodes of the mesh.
Okay. And if you, okay, so you have, yeah, the finite element mesh, it's, so if you kept refining and refining your mesh, will you get more and more smaller and smaller holes? I mean, will it have sort of a fractal structure where you have, because you've shown some examples where voids are used to let's say, decrease the weight without compromising the stiffness of that. So does it go on? Is this fractal if you keep refining your mesh?
If you keep refining the mesh, and generally, if you don't have a control in the scale, if you're obtaining a thinner and thinner bars, that's correct. And that's one big topic in topology optimization, which is existence of solutions. But this problem is already solved, okay? Maybe here I didn't mention, but when we implement compliance constraints, we solve the elastic problem for this problem. In which sense, no? This is the elastic problem in which sense. The elastic tensor is interpolated in the gray areas, no? For density and level set, we are working with a filtered field. So we filter, the G filter basically means I pass from here to here. And then maybe I can use a fixed epsilon. So the filter basically performs a convolution operation at each point and then even if I'm refining at some point, if I use a fixed epsilon of 2 centimeters, for instance, then at some point I should start obtaining thinner and thinner solutions.
More questions? No. I was a bit like, I'm not sure I understood all these creations that you have here.
Yes.
Yes. And their implication for the validity of the method. I don't know if you could explain that in simpler terms, like globally, how you, if you're fine with this, and what do you, and if not, how are you going to address it? Because you did mention something at the end in the conclusion, right?
Okay, yes.
So if you can,
yes.
Just, I know it's a hard question, maybe to try to summarize it in simple terms for someone like me that doesn't know about topology optimization, the details of all the maths behind it.
How I would address this issue, no?
And what it means, what this issue means.
Yeah. So this issue means that for level set with topological derivatives, we don't have a control in the maximum value of eta that can be used. Eta, remember, is the parameter that multiplies the range step flow. So the
yes, I remember those.
The one which goes to the constraint. So we don't have a control in the maximum eta, and maybe I'm using a high eta, and then maybe I can put this here. So this is now density, but it can help me to introduce this problem. So the geometrical rate, the constraint evolution, and yields this expression here. So if eta is very, very high and I don't have a control, I can see here that jk plus 1 is basically gk multiplied by some number, which if eta is very large, maybe I'll think something like this, no? Gk plus 1 is equal to 8 times gk. So that's why I'm going to 0. Yes, I am. I've taken these associations because this
and it doesn't converge.
And it doesn't converge well.
So how do you know when you just stop the simulation?
How do I know when I reach
the final solution, or you don't reach something?
Here. No, I just run a fixed number of iterations.
Okay.
More or less, I mean, okay, with 1,000 probably I would converge with oscillations. So for level set, I should also for density, I know the maximum value of eta. For level set, I should study an asymptotic expansion of the constraint functional, but with topological derivatives and studying the level set, and it's quite complex. That's why we have not studied it yet. We prefer to use this analogy, as a first approach that more or less worked. But yeah, we should study with more detail the asymptotic expansion for the constraint. But yes, this happens basically because if you don't have a control of eta, then you are amplifying the constraint of the previous iteration by some number which is greater than 1 in absolute value.
And I have another question. At some point, you had a negative compliance. That's because it was a mechanism, right? Just from the physical point of view, you know. Yes, here, -24. This means that it has what? Is it related to the negative?
Yes. Yes. So we can review maybe the physical definition of the compliant mechanisms. So the original compliance is external forces times the displacement. The incompliant mechanisms is not an external force; it's a field defined by the user, K, in the boundary, P. So I'm saying in the whole boundary, I want in some locations defined by this field K, where I want to invert the displacement, but it's not a flexibility.
Okay.
Okay.
Okay. Yes. Good. Okay. More questions? Anyone? No, everything's super clear. Well, you can always ask Jose over coffee later. Well, then we leave it here, no? Thank you, Jose.
Okay.
Thank you everyone for coming, and see you around.